going to record so that people who aren't here can watch it later. And basically, I run the whole thing from this iPad. So hopefully it goes well. Okay. I'm going to start by covering homework 2. And I'm going to start with, were there questions about questions 1 through 4, the stuff that he covered in class? Yeah.
The normal planar, oxygen, oxygen sharing electron, double bonded oxygen.
This one.
That one.
Yeah. Okay, that's as full screen as I can make it. What's up?
There was something with the sharing the electrons that didn't. Yeah.
So
That one left.
yes.
How is that one?
Resonance. So resonance is basically the idea of electrons are not stagnant. We draw them as such because I can't draw a moving picture. But in real life, electrons are constantly moving throughout the whole molecule. Particularly when you have like lone pairs near a double bond, those are all called pi electrons. And so they get shared between each other more easily. So what happens with an amide, which is a functional group you guys should know. This is so loud to me. Okay. So an amide is always going to be a nitrogen next to that double bonded oxygen. This part here is called an amide. And what happens is that lone pair moves like that, and you have a resonance form. That looks like that. And when it's in this form, it's planar. And we draw it usually like this, but it can exist as both. And so that's why both exist. And it's rapidly changing between those all the time. So although we mostly draw it as the amide, it can exist as trigonal planar. And so we always say it's trigonal planar. Yes. That is a very rare occurrence where you have something that looks trigonal pyramidal and it's actually trigonal planar. And it will only really ever happen when you have those resonance forms. For our class, it will mostly only happen with an amide. With an amide or aromaticity, but we have not covered aromaticity fully yet. So that will come later. What's up? Yes. So the rules on that in general are 2 rings next to each other, which was an example in, I think, the other homework or maybe some other lecture slides. That keeps it like sterically bound the way it is. And a 5-membered ring is big enough that they can split. So that's why this one is unstable. So if it was like something like that, where it's 2 rings and the nitrogen is the one that connects the 2 rings, this, as I have it currently drawn, is not chiral because all of those things are the same. But if I like add some other things that makes them unique, then it's chiral. And it's stable. This cannot, none of that can move around. for the same reason as the question we had before. It is trigonal planar, not trigonal pyramidal. And it needs to be tetrahedral / trigonal pyramidal to be chiral. Yeah. Was there a question? Yes. So the question was about if this is stable or unstable. And if it counts as a chiral sector. Yeah. Can you talk like a smidge louder? The fatter end. The thicker end is the one that is like going in or out. And the point is the planar one. Yes. So if I'm you, the wedges are coming towards us and the dashes are going in. With which? So it would be the whole, this whole part. Because we have this that's sending it out and this that's sending it out. So this whole part would be out towards.
You mentioned something flat. That.
Can you be more specific with your question?
So he somebody mentioned something about that. It's like we're not gonna go there. So there's something about nitrogen and whether or not it's a part of it going in or out of the frame, whether it's perimeter or perimeter or
I'm still not sure I totally follow. Okay. Okay. We'll table it. If you can figure out another way to word it, or maybe like point to an example, I might be able to help better. Other questions? Comments, concerns? What's up? Everything? It really depends on your strong suit as a student. Like some people really easily can see stuff in 3D in their head and they get chirality like that. Some people do not get it. And so it really depends where your strong suits lie. I do have some practice problems for us to do after we finish covering the homework. What's up? Can you be more specific? I do have some practice problems about calculations, yes. But I do want to cover the homework before I get to those, because he promised, or he told everyone that I would do that. Yeah. Yes. That depends what it was when you started. So for those who didn't hear, her question was, a conjugate base, once you lose the proton, is it positive? If it was neutral, yes. But if it started with a charge, that charge will reflect it. Also, I'm pretty sure it's not positive. I'm pretty sure it ends up negative. Yeah. It's not losing an electron, it's losing a proton. So the hydrogen is a proton and a neutron, but it's not taking the electron with it. And so a proton like the idea of a proton is really H plus. And that means that it's a hydrogen that is not moving with any electrons. Yes. So what you're losing is H plus, and H plus is what's going to the other molecule. Yeah. If you had asked me that 20 minutes ago, I would have uploaded it before I started this, but we're in too deep now. I do always upload like this notability thing that I'm writing on. I always upload this when I upload the office hours. So you'll have that by the end of the night. What's up? Canvas, there's a module that says just as resources. Everything I upload will, yeah, that long doc, you're gonna use that all semester. So trigonal planar means double bond. That's an easy way to remember with nitrogen. If there's a double bond, it's planar. Yes. There's no electron cloud. So it's flat. Yes. If you're talking about resonance, they have to share a carbon. That is one way that a nitrogen can be trigonal planar. Yes. Or the nitrogen itself can truly have a double bond. Yeah.
Question two. I know that's based on pKa's. Are we gonna have those exact molecule pKa's, or are we gonna have to start combining and adding them together?
So you'll be given a molecule that has one main functional group to think about when you have a question like this. And you will be using your table to find the closest match to that functional group. Getting this concept of like closest match down now is important because later when we learn NMR, we're going to do the same kind of thing where you're looking for a pattern to match to an NMR table. And you will be given the pKa table. It's the same one as is in lecture 8, I believe. Yeah. Yes. Yes. Other questions? What's up? Yes. The conjugate base is just losing your acidic proton. So if we look at the actual structures, once you identify an acidic proton, your conjugate base is that same structure, just without that proton. There are no dumb questions. Your pKa table. Yes. Yeah. If you don't copy it exactly as this molecule, so like thiol, which is SH, I believe is on there. And so if you were to just draw this as like R S minus, I'd say that that gives you almost full, if not full credit. What's up? It really depends what that carbon is attached to. Yes, but what are the other 3 bonds that carbon has? Yeah. So it really depends. Because like an alkyne and alkene have different acidities, and both of those are just carbon hydrogen bonds. When I said alkyne and alkene, anybody know what I'm talking about? I heard one-ish and just mutters outside of that.
But I'm not like saying.
Alkyne is a triple bonded C. Alkene is a double bonded carbon. And they have different acidities, but these are both carbon hydrogen molecules. So your first instinct with acidic protons should be heteroatoms, but that's not always necessarily the case. Other questions? Yeah. I will go over every question between 5 and 10. Once I finish the questions outside of that. Yeah. Mhm. Yes. Other questions? If not, I'm going to start covering question 5 through 10. What's your question? Closest guess. For these, they're usually smaller molecules and you might be able to find the exact match. But it'll probably be closest. What's up? Yes. Point to the higher pKa. What's up? Yeah, I can draw all of these ones. Are there more than these ones that you would like? He does have a slide in one of the lectures that has the functional groups you should know. Probably. Okay, I have this document that I have not yet uploaded for your year yet because it can be scary to look at. I usually upload this between your last exam and the final. But this is like, if you didn't show up for class all semester and wanted to make a 45 on the final to pass the class, you would use this. Which you guys are all here, so you're not gonna do that, right? You're like gonna actually try on the exams and stuff. And this has all of the reactions you're gonna learn and detail about them. So like what exactly is going on. And I realized that maybe I should upload this now because at the end, I do have a list of functional groups to know. That's what 8 years as a chemist will do to you. Perfection is not important. If I can look at it and know what it is, that's what's important. You also, I'm gonna upload this. I realize now that I should have just uploaded it at the beginning, but I'll upload it whenever we're done here. I don't have the authority to say this is a definitive list because I don't know what he's gonna put on the exams. Yeah, I mean, he chose that slide on purpose. Okay. Yes, let's get through the homework. So true. Okay. Yeah. If you whisper my name ominously, it will call me to attention. And then you don't even have the question ready? That's crazy.
It's possible.
Oh, yeah. But nowhere. Like one that's like.
That's so true. I don't know. That's not a question. That's a statement, and it's true. The ones that get mentioned, learn them. $12, that's a great number. Do 12 then. Listen, your pKa table is like a cheat sheet of functional groups. It has all the names on there and then shows exactly what the structure is.
Okay. Table is our best friend.
Yes. Yes. The pKa table itself has the names of the functional group with their pKa. Like it'll say protonated amine, and then it'll have a picture of an amine. And you can go, that's what an amine is. So if you get a question, and you should pay attention, if you get a question like this, and you see a word and you're like, I don't know what an ester is, look at the pKa table. It's gonna say ester, and then it's gonna have a drawing of an ester. That'll get you, hey, at least partial credit. And I'm not gonna lie, partial credit really gonna get you through this class. So, back to the task at hand. Do you guys want me to cover question 5, or were people here for, I can't remember where he left off. This is where we left off. Okay, so this was his prank question. None of them are identical to A. None of them are identical to A. I will draw you an identical one. Okay, so can I get thumbs up, thumbs middle, thumbs down on how you guys felt doing this question? Cool. Wow, overwhelming answer. See how he put this big thing that says make models? He low-key onto something. Make a model. If you don't have a model set, find someone who does have a model set and make one of these to borrow for the semester. One of these is a carbon center that has 4 different colors on it. That way, when you get a question like this, you can say, okay, this one is green, and this one is red, and this one is blue.
You found it.
Okay, if you want the functional group slide, it's lecture 7. So with this, I'm gonna need to clip this because I need both hands.
Do you have tricky questions like that on a test where it's like, hey,
No. His tests are more straightforward than that. What is the question in the back? What's up? Sure. Yeah. I'm gonna be so real with you. Neither him nor I will be there. Don't cheat though, because there will be proctors and they'll tell on you. Yes. You are allowed to bring models. Yeah. You can have the models and a calculator. I will be there for the people who have accommodations. Word. Okay, so back to the question at hand. If you make something like this, this will help you with all of these kind of chiral questions. Okay, so I hate this microphone. So true. That's just gonna have to be good. Okay, so you have something like this, right? And I have said that black and green are CH3 and CF3. So if I make this look exactly like it is up there, that's me. Okay, yeah. So black and green are in the plane. They're flat. right? And then we have red going backwards because hydrogen is going backwards, and blue for bromine is going frontways. Now, comparing A to B, CF3 stays in plane in both. So I'm going to hold on to that one. And then all I'm going to do is twist. So now this has the hydrogen in plane. We don't want the hydrogen in plane. We want the bromine in plane. Now that the bromine is in plane, that means that the red hydrogen should be wedged because it's coming out, and the green CH3 should be dashed. Is that what's written up there? Is it the exact opposite? So they're enantiomers. Now, if I were to take the mirror image of this, it's right. That is exactly how it's drawn up there. That's how an enantiomer looks. So, putting it back the right way, we then can compare B and C. We know that A and B are enantiomers. Let's compare B and C. Again, we're going to keep hold of the black one, that is our CF3. And we are now going to turn so that CH3 is in plane. Well, this red is facing backwards, so it should be a dash. And this blue is facing frontwards, it should be a wedge. Is that what we have written up there? Did I say that right? No. Hold on. It should be blue. Oh, because I still have it flipped from when I flipped it. Okay. Black and green in plane. Red backwards. Yes. If there was this kind of question on the exam. So we know that A and B are enantiomers. I had to flip this to make B. That's how I ended up mixed up. We flipped it to make B. What's up? So you're talking about how to solve this and like not with the model by looking at this, which we can do.
I know that are on the F.
I picked that one because it's in plane in both of them. Well, CH3 is not in plane.
Oh, got it. Big thing.
CF3 is in plane in both of them. That's why that's the one I hold on to. Everything else is going to turn. CF3.
Yeah.
Other questions, comments, concerns? What's up? Yes. So if you don't have a model, we're looking for the switching of two things. So between A and B, CH3 and BR got switched. So now this is in plane and this is coming out of the screen. Because you switched those two, they're an enantiomer. With this one, we switched PR and H. Here, I'll write PR. And then with A and D, we switched BR and CF3. So when you have something that's identical, this is identical to A. And that's because there's not two that we can switch. Drop this a little. There's more than two switched there. It's really just three have turned. What's up? If you the vague wording on that can go two ways. If you're talking about switching like this, switching once will get you in an enantiomer, and then if we did this and switched again, you get back to identity. Wait, that's not drawn right. Ignore that. But it's like, if you take the mirror image of something, you have enantiomers. If you take the mirror image of the mirror image, you end up back at the beginning. What's up? Yeah. That is neither enantiomer nor identical, because it doesn't have the same four things. You gotta have the exact same four things for them to be considered enantiomers or identical. What's up? Yeah. What? That's one of these. The dashed line. Other questions, comments, concerns? This stuff is good to know, but not a priority for right now. Am I good to move to question 6? No.
Actually, a small question for the, on 6 question. That green, it's kind of like diagonally into the plane, but I continue to show that as going into the plane on, or what I can do.
When you're just doing a 2D structure, you will have no wedges or dashes. It'll all just be straight lines. Like that.
Oh. God. Spent so much time trying to figure out that angle.
That is when you do a wedge or a dash, that is indicating a 3D structure. So if you are tasked with only drawing a 2D structure, you do not need wedge nor dash. Yeah. What's up? No. As long as your hydrogens make sense. What do you mean?
That top level. 3D structure, does that
These are the same hydrogen.
Yeah.
Oh, that means the same thing. You're good. Like, O dash, you did this instead.
Yeah.
That means the same thing. What's up? Yeah. Switched which way? Like, so CF3 stays in the plane, bromine is in the plane, and then what do you have facing in or out? Yes. That would be identical. Okay, question 6. Question 6 should be straightforward. Were there questions about? Oh, yes. Okay. You can write it as H2. You could write it as these two coming out. As, you just have to indicate in some way that there are two hydrogens. Oh, you mean like you didn't indicate hydrogens with the gray ones, but you do with the blue ones? Yes. So the whole idea of skeletal structures is that you are not explicitly writing out any carbons or hydrogens. But that difference comes with heteroatoms. So you have to specify if they're attached to a nitrogen or an oxygen or a sulfur or a phosphorus. Yeah. Sure. That's fine. Like you had it switched like that. That's fine. It's an aromatic ring. We'll learn. We kind of have already covered what aromaticity is and how those bonds are constantly like moving. But that's, aromaticity is not a concept you need to know. Yes. What's up? Yeah, there are functional groups in this one. Does anyone want to take a stab at some? Alcohol. That's so true. This is not rubbing alcohol. This is too complex of a model. What's up? What's it called? Really close. One letter off. E. And then these two rings, you don't have to worry about. They have fancy titles, but you don't have to think about them. Okay, other questions? Yeah. It does. If you write the H as the connecting bit, like if you wrote, that would be wrong because that's implying that the hydrogen is the connector. Hydrogens should always be terminal because they are only making one bond.
Okay, wait, I did.
Yes. Well, it's not always the first one you write, because if I wrote something like this, I wrote hydrogen first here, but last here.
Okay.
But it's because you want to write it to the connecting bit. So we wouldn't write, well, sometimes we do write this, but this is more correct.
Okay.
Yeah. That's because amines, huge blanket term. You can have primary, secondary, and tertiary amines, and that tells you how many carbons it's attached to. This is a tertiary. And this, you do not have to specify this as secondary. A nitrogen and a carbon. At least one carbon.
So that's a section.
Oh, that's an amine. You're right. Double bonded oxygen. Other question? Yeah. The difference between an amine and an amide is a double bonded oxygen. Amines are just carbon and nitrogen. An amide means that next door is a double bonded oxygen. There's one carbon that is attached to both a nitrogen and a double bonded oxygen. Moving on.
Questions are you covering? Right now?
I was about to move to 7, unless there's more questions about 6. Great. And I did see the 6 Sept vector in today. Okay, 4 differences between the following 2 structures. Can I get thumbs up, middle, down on how we felt about this question?
The only thing
I'm so hoping to only see thumbs up. Spot the difference? Should be easy, guys.
You could just see it, right?
All you had to do was circle it. So we had a methyl group here that is not here. We had a change in the 3D chemistry. We had a double bond that disappeared. And we had two methyl groups that disappeared. Questions, comments, concerns on this one? Yeah. Yes. Where did I circle that? This whole file will be uploaded at the end of this. You can look at it for as long as you'd like. Yes, an amide has a double bonded oxygen. So this one carbon is attached to both a nitrogen and a double bonded oxygen. Whereas an amine is just a nitrogen that is attached to at least one carbon. And I move on. Okay. Question 8. How do we feel about this one? Middle down. Okay.
I feel better now that I know that it's identify.
Yes.
That was my biggest issue, trying to apply.
I got to practice problem about this.
Got it.
So for this one, you had to use the internet a little bit. That is something you'll see in a lot of the homework because he knows that you are not necessarily going to use every aspect of this class in your real life, but you will probably need the internet. And so learning how to use the internet to manage questions like this is part of what you learn in this class. So look up the structure and acid structure of the acid and conjugate base for the chess buffer. And then you look up the pKa, which was in the slides. Look up.
So the acid that I found for tech, they put the acid on the SO3.
Yeah.
But this one, the acid, the H plus on the N.
That
That
no, not wrong. You may notice that this range kind of big. That's because you're going to lose hydrogens here and here, depending on your pH.
I would also have to acid. So,
Conjugate base. Conjugate.
yeah, so it says conjugate base, like the acid and base, but in part E, it says an acid of the conjugate acid and acid. Because I thought, no. Okay.
You can low-key just ignore that word in this case. Because in every acid-base pairing, you will have a situation where you see the acid form and make the conjugate base, and you see the base form and make the conjugate acid. It just depends how the reaction is written. Yeah. No. It would give you a structure, and then you might draw the conjugate base of that structure. Yes. No, you don't have to memorize any structures at all. It will say, draw the conjugate base of this structure. You're going to remove the acidic proton. The acidic proton is, so that's like question 4. Question 4 and looking at this are covering the same concept. One is just looking at loose molecules and the other is looking at a buffer system. Which, a buffer system is the mix of an acid and its conjugate base. It's the two forms, sometimes multiple forms, depending on how many protonation states there are. But the key thing to remember is it is an acid and it's conjugate base. Ominous looks around the room. Okay. What's up?
That one, I think we'll do both. I drew one with the, I drew one with the.
That's fine.
So like, is it?
If there are multiple protonation states, like this one, where you could then do it again. Well, I only drew this one in because it came up in a question. You only have to draw one. If I remember correctly, you won't be given so many options if it were on it. Yes, acid-base chemistry is always the movement of a hydrogen. Yeah. For just drawing a conjugate base, no.
Okay, like the one.
Yep. You just draw what the product is. No like arrow pushing. Or the curling arrow mechanism. That's what you call it. Yeah.
So my question, lastly,
Is it better aligned with another topic that we might cover later? Okay.
so if they have heard it.
Yeah.
So that's why we're not.
Those are the same thing. The mirror image, two constituents flipping is a way of breaking bonds to make the mirror. Yes. Okay. Other questions on this one? Yes. So like if we were to do the arrow pushing of this, you're gonna have something that takes the H plus, and these electrons that are in this bond are gonna go to the nitrogen. So that's why it starts positive and ends neutral, because the electrons that were once in the bond to the proton are now back to the nitrogen, and that is how your electron changes between the two. Yeah. We'll get to question 10. We'll get to question 10. Does it apply more to this or to question 10? Okay. Yeah. Don't worry about that right now. Other questions about this one in particular, or can we move on? Great. It's gonna be so real, that's fine. Do we need more guidance on this question? There will not be a question like this on your exam because you don't have the slides in front of you. Great.
Yes.
This one, you should know how to do.
That's all I. What about,
I don't have 20 practice problems over this. I have some practice problems over this. So the important equation to know is pH equals negative log of H plus concentration. H plus concentration, that is your acid. Those are the protons coming off of your acid. He gave you a couple different formulas. That's the Henderson-Hasselbalch equation. I don't think you will need that.
About strong acids that fully associate, or will he give us the acid and like, is there a way to do this with just the number of moles of weak acid? But there's not a way.
No,
So,
you will either do strong acid or you will do buffer size. let's focus on this one, and then we'll get to practice problems, and you can ask about the other equations. So with this one, something that I feel like people don't remember. Can anybody tell me how he gets from this to this? How do you like knock out log when you're doing something on both sides of the equation? 10 to the power. So this he just solves for negative log. But if we had been given a pH and you're finding the concentration, how would you do that? How would you isolate your X from a negative log? What is the inverse of negative log? 10 to the power. So you would do 10 to the negative, because we have that negative there. 10 to the power of -7 equals X. So when you remember pH equals negative log of H plus, you can also remember that 10 to the negative power of pH equals H plus.
Either now or we have this equation and we have to go right out to like find out how many moles of whatever or something like that.
Probably not.
Okay.
That's a lot of math for a 15-minute exam.
Okay. So H plus
Yeah.
forever.
That is the inverse of this equation. So with these, you just plug in the information you're given and solve. You will need a calculator on the exam. If you don't have one and you leave the answer as this, I will give you partial credit. But you should have it as a calculator. Or borrow the person next to you. Yeah, I'll tell them to. Yes, calculator and models, and some kind of writing utensil. That's what you should have for Friday.
So say like 10 to the -7, zero point three or whatever, point one. We can just put 1 times 10 to the -7, right? We don't have to write out the zero.
Yeah.
Okay.
What's up? Yeah. You will not be judged on your work. You are judged on your answer, and if it's wrong, then I will look at your work and say, what happened here? And try to get partial credit somewhere. Yeah, you always want to be in molar and not millimolar, which you will most likely always be given stuff in millimolar. And to the point of this, where you have like 10 to the -7, you could also report that number in millimole or micromolar.
Oh, okay. Would that be a more acceptable answer?
Yes.
Okay. That would like that point.
Yeah. Which the difference between molar and millimolar is 1,000, and millimolar and micromolar is another 1,000. I mean, these two equations are the same thing. It's just isolating X on one side versus the other side. So if you're solving for H plus or you're solving for pH, one might be easier to write down first. Can I move to practice questions, or do we have more questions about this? Great. Here's your first practice question. This was 10. I don't know what to tell you other than it's a factor of 1,000.
Divided by 1,000.
Yep. Don't worry about kilo. You will know, you need to know milli and maybe micro, but definitely milli. Milli. Here's the first practice question I have for y'all. I got a random molecule, add the missing hydrogens, identify the stereochemistry of the highlighted atoms, and identify the chiral centers. And then I'm gonna have some brave people come up here and solve it on the iPad. Hopefully, if there's any volunteers. The way I can see that your camera is covered by the case of the iPad and you're holding it up like this. What? Because you want to identify the stereochemistry of the highlighted atoms, and that's going to be hard to do if there's no highlighted atoms. How long do you feel like you guys need for this question? Because keep in mind, your exam on Friday is 50 minutes. Which I did have to remind him that the exam was 50 minutes and not an hour and 15, and he cut stuff from the exam. Yeah, well, he gave me the exam and he was like, "Can you proofread this?" And I was like, "You know that this class is 50 minutes because it's Monday, Wednesday, Friday. Because usually we teach." He was like, "I forgot about that." They'll always be that way, whether you're a he went from 6 to 5. Yeah, the idea of 5 questions is fake. Like each question is really divided up into multiple parts, which are basically their own question. So it's really 5 major concepts encapsulated in a variety of questions. This whole PDF. Yes. The PDF will be uploaded at the end. So it will have all of my scribbles. Like today, my exam reviews are you decide the end time. I stay here until everyone has their questions answered. I said I was here till 10. 2 and 10 are not the same thing. No, I would not stay here till midnight. I also usually do these the night before the exam, and this is the first semester I'm trying them 2 days before the exam in hopes that you guys like retain the information and not just cram. We'll see how it goes. Do we feel good about hydrogens? Does someone want to come draw the hydrogens? Yeah? That's fine. I would not recommend it if you have the room. H2 is a gas that usually stands alone. I would go ahead and just write them. H and H. I agree with all but one. Oh. No. Do we agree? Yes. Great. What do we think about stereochemistry of the highlighted atom? What's this one? Trigonal planar. What's this one? What's this one? Trigonal planar. What's the oxygen? So true. No. Yes. So your heteroatoms, which is like anything other than carbon, the hydrogens have to be explicit. They have to be like written out.
Okay, just me.
Yeah. Okay, what about this nitrogen? Trigonal pyramidal. Do we all agree? Do we have questions about how those were assigned? Yeah. Yes. If there's only one double bond, yes. If you have multiple double bonds, you got something else going on. Tetrahedral is 4 bonds. Trigonal pyramidal is 3 bonds, 1 lone pair. Yeah. Rings. Yes, it is. So, yeah. Yes. Yeah. Yes. Yep. Other questions? Okay, how many chiral centers do I have? Who wants to come draw them or like indicate them? I got somebody volunteering his friend. His friend does not look like he wants to do it. Yeah? Come take my dented Apple pencil. It is not 0.
Do you
Yeah.
want-
Yes.
Even though it has like with a constituent or just carbon.
but they're unique carbons. This one is attached to the phenyl group, and this one is attached to more carbon hydrogen bonds.
Okay, because this one I get, it's just like these.
This one is only like 2 carbons away from this chain, and this is 4 carbons.
Okay. That would be stable.
Yes, that would be a stable one.
This also blue.
Mm-hmm. Mm-hmm. I did not say how much there were.
I heard some of it.
Is that a question or a statement? You'd be correct. If the. Yeah, I can't hear you. So if people could be less loud, thank you so much. Please repeat your question. Because if you just think about them as CH2, you are ignoring the rest of the molecule. And this CH2 is closer to this, to this, to this, whereas this CH2 has another CH2 to a CH1 till it finally gets over there. So they see different things. And because of that, they are chemically different. Like if this bond were broken?
No, like if that, the whole top group of the CO bond,
Like if this bond were broken?
yes. Or would it still be different?
If that bond were broken, it would not be chiral,
Okay,
because these would be the same.
okay.
Yeah. It has to be trigonal pyramidal. Yes. Yeah. It's labeled as stable because sometimes nitrogen can have unstable chiral centers, not because the rest that are written here are unstable. Yeah. No. Yeah. What do you mean them? Like all of them? So our number 1 rule for chiral centers is we need to have 4 unique substituents. If you think about it as just the neighboring carbon, you are missing a bunch of chiral centers. Because we are not just looking at the next closest atom, we are looking at everything that's connected through the whole molecule that way. Yep. Yep. An easier way to do it is to look at it symmetrical. If I could like print this on a piece of paper and fold it and it perfectly aligns with like these complex ring systems, if it perfectly aligns, That means they're exactly identical on both sides, and it's not chiral. Because they are not. Yeah. Does it have 4 substituents? That's your A1 rule for chirality, is 4 substituents. And this carbon has 1, 2, 3. If there is a double bond, it cannot be chiral. Yeah. Can you speak louder, or can other people not speak? Yep. Yeah. So what he was getting at with that is that you keep looking down until you find a difference or you get to the end. Yeah. This is trigonal pyramidal, which is a type of tetrahedron. So if we go back to the slide where we learned geometries, you have electron geometries and molecular geometries. And tetrahedral is like a blanket statement that can include trigonal pyramidal and true tetrahedral, in the same way that bent is sometimes an oxygen in the middle of a chain and sometimes a carbon with double bond. Yeah. Yeah. Either way, it's different. That's what makes it unique. Does that help? Okay. Yeah. Only with nitrogen. Don't worry about sulfur being chiral. Yes, sulfur also is weird and can sometimes have 5 bonds, so don't worry about sulfur. Other questions, comments, concerns? Great. Here's practice problem number 2. Eight, I believe. 7. Can anyone tell me what functional group they're looking at with number 1? Is a double bond a proton? So can the double bond be a proton?
No.
Okay.
So what,
There are hydrogens on this molecule. What's up? I am currently looking at the table and I see the listing for ketone. There are 2 pages. Yes. No. You're looking for this thing that has the red and the blue structures on it. That red and blue thing is the exact thing that will be printed for your exam. Does this carbon have any hydrogens?
no, so it has to be one of those. What is that like?
Seven or 8, it's in either.
7, 8, 16, 17.
Are we ready? Okay. I hope that that is not the case. So what is our functional group we're looking at with the second one? It's an alcohol, but we have a specific descriptive word in front of it. What'd you say? Alcohols are automatically protonated, but a protonated alcohol would be like an extra proton. Yeah, well, we're looking at the, yes. It is tertiary. This is a tertiary alcohol. And that's important because whether it's primary, secondary, tertiary is going to change the pH or the pKa. You know, based on how many carbons it's attached to. So this carbon is the like parent of the alcohol, and it has 1, 2, 3 carbon neighbors. That makes it a tertiary. So if you had something like this parent carbon is only attached to 1 other carbon, that's a primary alcohol. Yes. I'm not going to ask what functional group number 3 is because the whole molecule is functional. So we'll get to that one when we go over that. What about number 4? Yeah. An alkyne. And what about number 5? Any old amine? Yeah, whoever said that. Yes. Protonated amine. It have proton.
That's-
It have extra proton.
Oh, yeah.
Because it has 3 bonds, and instead of having 3 bonds in a lone pair, it has 3 bonds to carbon and a hydrogen. Does anyone feel brave enough to come identify the acidic proton of the ketone? You just pick one to do now. Don't circle the carbon. You're on the right track, but you have circled a carbon and you're identifying proton. So you have one extra step to do with this one that you don't have to do. You just have to draw the proton. Oh. Those are all right. So, with our ketone, we will pull one of the neighboring protons. Questions, comments, concerns? Yeah. Hydrogen equal proton for the sake of this class always. What's up? Hydronium ion, yes. Yeah. The resonance with the conjugate base can reach the neighboring carbons. It cannot reach those bottom carbons. So when we pull off the proton, and this is kind of getting into part 4 with the conjugate base. Immediately when you pull it off, it looks like that, but it has resonance. To look like this, or actually, and that resonance makes it stable. But that resonance, if we took off the bottom one, there are no resonance structures for this. We cannot move those electrons around because these carbons are all trapped up. Yes. The main gist is it's too far away. With this, it's looking at resonance. And so we don't have any other pi electrons being any lone pair or double bond that could connect that bridge. And so it has to be the neighboring ones in this case. Other questions? How do we feel about the other ones? The tertiary alcohol? Yeah. Because it is a tertiary amine that is protonated. So a protonated amine just means that it has a positive charge. Like it has one extra proton than it should. So with nitrogen, that'll always be N+. So if you see H, any amount of H's, N+, that will be your protonated amine. Means it has one extra proton than it's happy with. Yeah. Any of them will work in the same way that any of the 4 on the ketone will work. Either would be correct. Yes. Other questions, comments, concerns with this? Yeah. Mhm. Yes. Well, you have correctly identified pK for this one is 18 to 21. Can you tell me for the tertiary alcohol? 18. Hydronium? -1.7. Alkyne? Protonated amine? So now if we were to rank acidity, what is the most acidic? Hydronium. What is the next most? Next. Mhm. Yep. Questions on how I got here? It'll either say increasing or decreasing. Yeah. This is decreasing because we started with the most. Other questions? Great. Conjugate bases. Drawing a conjugate base means removing that acidic proton. So we already did that for the ketone, but for our tertiary alcohol, we can start with the normal structure. We're then going to remove our proton, but in removing our proton, those electrons had to go somewhere. O-. That's fine. We remove the proton, we put the electrons back on the oxygen. We remove the proton, the electrons end up on the carbon. We remove the proton, the electrons go back. With the conjugate base, you are always moving in the negative direction. If you start with a positive, you'll end with a neutral. If you start with a neutral, you'll end with a negative. Because when you are deprotonating, you are taking away that proton, but keeping those electrons. Yeah. With this one? No, because these all have hydrogens. And if we made this a double bond, this carbon would then have 5 bonds. A tertiary alcohol on the chart just goes to O-. This one is a ketone, and this is where we make that double bond in the circle. That's okay. Yeah. Either will. And this, actually, that's a really good question, because last year, there was a question exactly like this on the exam, and the graders only marked one resonance form right. That is where you should submit a regrade request, because they are grading off the key, and sometimes they turn their chemistry brains off and don't go, oh, that's the same thing. So if that does happen and you catch it and you got points off, submit a regrade request, and I will make sure that you get those points. What?
Oh.
Are we ready for the next practice question? Great. Draw the product of these acid-base reactions and the correct arrow direction. What's the concept? No. Yes. What? Does anyone feel brave enough to try the first one up here? Your PKAs are right. Do you agree with this arrow? Correct. The only edit I would make is that it is a better habit to write your PKAs under your acids. So I would write 26 over here and 4.8 over here. Because what pKa is telling you is the strength of that hydrogen's bond. What's your question? Because it is more favorable to go in the opposite way. From what was in it. You always want to point, so this is why I said you should write the number under the acid, because you want to point at the bigger number, which is the weaker acid, because that means that you are dissociating your stronger acid. Questions on this one? Do we feel like it makes sense? What's up? Yes. I missed the last part of that question. Mm-hmm. It is acting as an acid if we were going in that direction. I'm not sure I follow. Okay. So a carboxylic acid is a stronger acid, and that's what this functional group is a stronger acid than an alkyne. So that means it would more easily lose its proton than an alkyne. And that's why the direction keeps the proton on the alkyne instead of on the carboxylic. Yes? Okay. Other questions? Yeah. So with this one, or with this set of examples, you have a negative and a positive that is showing you which way to go. So your negative, and this proton being like explicitly drawn, that's your like dead bringer. That's the proton that's gonna. Question 2. Do I have a brave soul to volunteer? Correct. Does everyone agree with this? Or do we have questions on how we got here? You agree? You agree? Agreement? Good to move to the next one? I'm surprised that you guys so quickly agree with this one, because there was disagreement on this when it was an exam question last year. Because did you do it the other way around, where your water was the acid? and you ended with a protonated ketone? Yes. So, that was an unforeseen correct answer. You shouldn't, but we ended up marking both right. This was the intended right one. With the information you are currently given, yes. Yeah. Those would be the two molecules we end up with. What's up? So part of it is pKa, the other part is hydronium is more stable than a protonated ketone. Yes, but there is a more correct answer in this case. Yes. Other questions? Who wants to do the last one? Come on up. Yeah, yeah. Yes, but there are implied hydrogens on that skeletal structure. So this is the same image or same structure as the ketone in our predict the acidic proton question. That was the last question. Just oxygen does require 2 lone pairs to be neutral. That doesn't mean it can't have less or more. You just have to make the charge reflect that. They are being taken from the carbons. But they end, the end product, if you, yes, yeah. For the second answer option, yeah. And that's why it's the less correct one, is because oxygen is not happy being positive, but can stand being negative. Yeah. Either would have been correct. If you did a double bonded oxygen and a anion on the carbon, that would also be correct. They're just resonance forms of each other. It's like the same principle as the thing we just did. It's okay. Does everyone agree? You should, because it's correct. Yes. We all agree with this? Do we have questions, comments, concerns about this one? Yeah. Yeah. Well, with this last one, only one of your molecules has protons. But with the other ones, if you did it this other way, like this way, you would write the other pKa. So you would write the pKa for a protonated ketone and water instead of a ketone and hydrogen. So with this one, depending on what you picked, to do with the answer is what you would write the pKa values for. But you always write the pKa value under the one that has the proton. Yes. Yeah. 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 Protonated amine is always going to be if the nitrogen has a positive charge with the proton. The whole gist of amine is, I think, where you might be getting tripped up, because amines can be primary, secondary, or tertiary, and the one drawn in the pKa table is primary, where it just has one carbon attached. But this is a tertiary where it has 3 carbons attached. Does that also clear it up for you? Okay. What's up? Yes. Either. Doesn't matter. Yeah. Oh, yep. Other questions? Moving on. Buffer question. You guys are gonna have so much fun with this one. Yay. I work here. Molecular weight. Yes. Who asked me that question? Yes. If you need the Henderson-Hasselbalch equation, which is the one that's written here, it will be given to you. If you are doing just a simple like pH equals negative log H plus or the inverse, that is not given to you. So those are equations you'll need to like memorize. I cannot verbatim answer what will or will not be on the exam. But sounds like you might want to wait until this is solved. We did do Henderson-Hasselbalch, yes. So I'm gonna start by filling in what we know into our equation. So our equation is pH equals pKa plus log of our base over our acid. We know what our pH is because it's here. We know what our pKa is because it's here. No, don't worry about some things. And then what is the other piece of information we have? acid. What do we have to do before we plug it into our equation? We have our equation. We will now solve for x. Is this my answer? What else do I need to do? What is our question asking for? Yes. So that is why you need the molecular weight. What's up? That would change how much VDM you need at the end. You would multiply by 3. Because this is how much you need for 1 liter. If you were doing 2 or 3 liters, you would multiply this to get how much you need for 2 or 3 liters. We are not changing our pH nor our pKa. Because we're adding VDM, not VDMH plus. We're adding base, not the acid. So we want the form that doesn't have the proton attached. What's up? It's not irrelevant. In this case, because it's 1, it seems irrelevant. It would be relevant if it was 2 or 3. You would just multiply this number by 2, and you would say, then it would just be in grams instead of grams per liter. Other questions about this one? Do we understand how to do this? What about the next one? Proton concentration. What equation do I need here? Somebody speak it to me. So 12 equals. What do I need to do to isolate my X? I don't feel like writing that out, so I'm just going to say that's my answer. No. You need units. This would be even beyond micro. What is that, nano? Doesn't matter. Don't worry about it. You could,
but like, that would,
yeah, this answer, right, too. Yes. I have just now decided it would. Okay. We feel good about that one? That one makes sense? Great. What about this one? Which one of the following acids is suitable for a pH 10.6 buffer? You will need your pKa table. Let's take baby steps to get there. You are correct, though. The first thing we want to do is identify the pKa for all of these. So what is the pKa of this first one?
I
5.2. This is a protonated purity. Protonated purity. What about the second one? .8. What functional group is this? A carboxylic acid. In teaching this class, man, have I seen some crazy ways to spell carboxylic. Spelling does not matter. Okay, and what about the last one? What is the pKa? And what functional group is this? Protonated amine. This is our correct answer. Because that pKa is close to the pH that we want to buffer at. Yes, we agree? We're ready to move on? I only have the annotated one.
What?
I only have the annotated one. So, this is the last practice question I have for you. Draw a molecule with the following: an amide, an ester, an ether, a phosphate, a carboxylic acid, a ketone, and an alcohol, and have at least 2 chiral centers. Desks at an awkward height to sit at. I'm gonna give people a minute to do their own, and then yes, you can do it. This is fire. What? Yes. Well, the homework is not graded on correctness, so don't worry. No. It doesn't necessarily need to be isolated, but like if I put an alcohol next to a ketone, I have now created a carboxylic acid. So you want to avoid things like that. You will get it on exams where it's necessary. Are you ready to come draw yours? Oh, you got the list of functional groups and you're going for it.
I'm looking at the PKA chart.
Okay.
That is allowed.
Okay.
Looking at the PKA charts. It says amides look like.
You gotta draw a molecule that connects all of them.
I will.
Okay.
This is how I do my sauce. That's great. I am missing two things. So it's not on the chart. Can I submit? I don't have much numbers memorized. But I did my best. And I will also kind of look at like the chart branches and stuff, or like certain atoms be more bonds. Oh, what's so wrong?
You got an H in the middle. You got an oxygen with what looks like 4 bonds. I'm gonna give you guys a life hack on how to do these questions really easily. We're gonna start with a ring. You have a starting point where you can now just branch off the functional groups you need. So I'm gonna start with an amide. I'm now gonna do an ester. Is that right? No. I'm gonna do an ether. I'm gonna do a phosphate group. Actually. You're gonna have to say that again. Nope. Skeletal structure means that all your hydrogens are implied. Phosphate group, carboxylic acid, an alcohol, and I need a ketone still, so. Now, to make this easier, and the sick thing about this chiral is that every one of the ones in the ring is a chiral center. Chiral, 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 chiral. You need at least 2. I've got 6. What's up? Yes. Yes. So what he was amending was when he had written a double bond, when you say just a double bond, that very well could just be this. That's a double bond. But that's not what he meant. What he meant was an alkene, which is a carbon-carbon double bond. And so that's what he was clarifying. The way that it was worded, you would get points for this double bond. But what he had been looking for was this kind of double bond. What's up? Yeah. Yep. Yep. What's up? That one, there should be a slide that says a bunch of functional groups on it. Some other ones to know are amine and thiol. And an amine is NH2 and a thiol is a sulfur and a hydrogen. Yeah. Yep, a skeletal structure is fine. What's up? If you say H2, that means you have 2 hydrogens. They are not unique. That cannot be a chiral center. Yeah. No, you don't even really need to know a phosphate right now. No. Other questions? These are all the practice problems I have. So if you have conceptual questions, now would be the time to ask them. If not, good luck on your exam. I will not see you. The proctors don't know about your exam, so they may not be helpful when you ask them questions. Good luck. What's up? You should know all the ones covered in these office hours. What's up? Yes,
So,
that
like,
blue and
worst
red
comes to
one.
worst, if I forget what a phosphate, whatever it is, can I just look at the PK?
Phosphate is
Yeah.
not in the PK. It's
Oh, sorry.
It won't. I wrote this question and I was not thinking about what kind of functional groups you need to know. Don't worry about phosphate. Yeah.
Like, worst comes to worst, we forget.
Yes.
Okay,
Yeah.
okay, thank you so much for all your.
What's up?
These things.
Yeah.
I still don't get why the arrows, like, why the arrows go that way and
Mhm.
go this way.
Mhm.
So like, I'm confused in this part. Like, why does it go this way instead of that way?
So the arrow is showing which direction is more energetically favorable. And it is easier to break the stronger acid than the weaker acid. Stronger acid is the lower pKa. So you always want to write your pKa's under the acidic form so that you know you always point towards a higher number.
So in this case, here, this would be.
Yes,
down
because
here.
this one is 26 and this one's 4.8.
Okay. And then one more question. This question, what was the question about the buffer? I forgot to.
It was which of these would be most suitable for a buffer at pH 10.6? Which one of the following acids is suitable for a pH of 10.6? The pKa is 10.6, and so that's the closest to the pH they're looking for. And the pKa is what gives us the prime pH range for it to act as buffer.
So what if it would be another, like, I don't know, another number.
So if the pH was 4.8, then this would be your answer. If the pH was 3, the carboxylic acid would still be your answer because that's the closest one to 3. In this one, they match perfectly, but you're looking for the closest.
And,
Yes. That'll be given. If you have to do Henderson-Hasselbalch, it'll be given.
thank you.
What's up? So. So with identifying the acidic proton. There. Yeah, because these questions might be helpful to other people. So. So, with identifying. A good starting place is hetero. So, with this one, yes. So, with these examples, you have this tertiary alcohol. Oxygen is a hetero atom, and it has a proton. With this one, all three of these are the same. And they're all attached with it. So all three hydrogens are identical and most of them. So they all could be. Yeah, okay. So you could circle all three, you could circle one. And then my strap for that would just be like negative. You'll only take one proton. Oh, okay. What about that one? So with this one, our hetero atom, well, so acidic proton, it has to be a proton. You need to find a hydrogen. And there's no hydrogen directly attached. Yeah. You go to the closest neighbor, there's also no hydrogen there. We go again to the closest neighbor, let's found hydrogen. Okay. That like every moment, like if there isn't a proton, so like there's no acidic proton here because there is no proton. That's fine, but there's no acidic proton because there is no proton. But any proton can eventually be acidic. So the conjugate base is just, once we take away the proton, the electrons are left. You have to drop. So with this one, we take off this proton. It can't like, and these electrons end up on that side. So we still have all of those implied hydrogens. Right, all these hydrogens, and then just write only one carbon, or do I have to write that? You have to write that, because that's the formal charge of this part. Okay. Thank you. Yeah, what's up?
So first one is, we need to be able to put PKA or is that going to be good?
Don't worry about it.
Okay, and then also, so for that one right there, is it, those are like resonance structures, right? So I can build on any of them?
Yes. So this is your conjugate base, and then this one I have circled below it is a resonance structure. So either of these two structures would be correct for this fourth part of drawing the conjugate base.
Okay, and then also, when like benzene rings, there's also like, if there's like a carbon double bond, and if the question wants us to label the alkenes, would I put that as alkenes, or I just say something different?
With benzene, we would say it's a benzene, because that whole thing, like this structure, has a lot of unique properties that make it its own thing.
And then is, so if we have to draw the enantiomers, can I just do the mirror image? Or I can do the, where I switch the wedge and the going in. And I don't have to do that whole thing on the homework where it's like kind of confusing, like switching a lot of stuff. So I can do that too.
And you elaborate.
So it's just like, I don't know, it seemed like more confusing because it wasn't just like switching the wedges, but it switched the atom. Like that bromine and the hydrogen, they're switched, but the wedges stay the same. So can you like also just switch the atoms without switching the wedges?
Yes.
Okay. So, okay, I think that's it. Thank you so much.
But I just have a question. I know you answered it, but I just need to clarify on the last question. So the double bonds, they would count, like in the that you had.
So if this question was asking, and double bond, you're already using these for two other functions. Okay. So you would need to have a third. Okay. If it was written vaguely as double bond, you could do hydrogen.
Okay. And you don't have to like add new molecules and or like
You got to make sure the formal charge is right.
okay.
Always with everything. Do oxygen, or you could just do a double bond.
Okay, that was it. Thank you.
What's up?
And so if we just didn't do that, you need that hydrogen to it.
Yes.
Okay. Let's do things. Is this technically an
Yes.
because
Well,
we have the mirror
no.
image and then it had the
No, because you're missing. So they're completely different.
anyway, and then this is the only one I can have. So is this one with these I think I fixed for those two are, but is that one? It does go to different things. The carbon?
what is the deal with that? Look at what is that, the planetary goes there, so. And you have a planar chiral center. So.
Okay, that was just, I was trying to like, it all comes back and I have to think about it again. And then these two, this one I think is, it's like those two, and then these two,
Is that a nitrogen?
yes.
I thought that was the same question.